In this lesson, we'll see three problems. The problems themselves are really simple, but the reason I'm showing them is to give you a kind of an idea as to what is the sequence of steps to solve problems on normal and tangential components. Let us look at the problems one by one real quick. Here problem 1, in which the pedal boat is traveling around a horizontal circular path with constant radius, rho is 50 meters, at a speed of v is 0.2 t square meters per second, where t is in seconds. We need to find the magnitude of boat's velocity and magnitude of its acceleration at time t is equal to 3 seconds, that is from starting time. Let us see how we do that step by step. First we need to find what is its tangential component of acceleration, which is vt dot, which is dv over dt evaluated at 3 seconds, that is 0.2 multiplied by 2 multiplied by 3, that is 1.2 meters per second square. Then we write velocity at time t is equal to 3 seconds, which is v3 is already given to be 0.2 multiplied by 3 square, that is 1.8 meters per second, that is the magnitude of the boat's velocity. And then its normal component is velocity at that instant squared divided by radius of curvature, which comes out to be 0.0468 meters per second square. And then we write total acceleration is normal acceleration square plus tangential acceleration square under square root. That will give us the total acceleration of the boat. So acceleration is 2.22 meters per second square, velocity is 1.8 meters per second square. It is really simple, but we just need to remember that total velocity is tangential to the path. Total acceleration has two components, tangential and normal, and the total acceleration is under square root sum of both of them. Let us quickly try to look at another example. This example may be just a little bit involved, but it's very clear if you follow through step by step. At this point A, the car has a speed of 25 meters per second square, and the driver hits the brake here, and it starts slowing down gradually as it goes from A to B and B to C. This B to C may be approximated to be a circular arc with an angle of theta, where theta is given to be 30 degrees, and we can approximate the radius of curvature to be 250 meters. We need to find what is its acceleration right about over here. Let us see how we do that. Step 1 we notice is, because acceleration is given in terms of distance, we need to know what is the distance traveled by the car as it goes from A to B and B to C. That is, distance from A to C we need to compute. Okay, that we can clearly see as straight line distance AB, that is 200 meters, but circular added to this circular arc distance BC. AB is 200 we have here, and BC is circular arc 250 multiplied by pi over 6, r multiplied by theta. So we have SAC as 330.9, total distance traveled from A to C, while it is decelerating with tangential acceleration given by the expression there. So first step we write is, what is the tangential acceleration? Tangential acceleration is given to be 0.001 multiplied by distance at that point minus 1. So by the time it reaches point C, the total distance traveled is SAC. So we write 0.001 multiplied by SAC minus 1. So by the time it reaches point C, its acceleration tangential component is minus 0.669, and To find the normal component of acceleration, we need to find the velocity of the car at point C, and then use normal component is vc square over rho. This rho is given to be 250, but velocity at C is what we need to find. To do that, we will use the known relationship AT into ds is v into dv, and we integrate from 0 to SAC. At A, S is equal to 0, then it traveled 200, and then r theta distance, the total distance is SAC. So the limits are 0 to SAC. The speed here is 25 and gradually slows down and comes to a speed of v subscript c. So the limits are 25 to c. So we got this vc to be 8.53 meters per second. Thus we can find normal component is vc square over rho 0.29 and total acceleration to be under root normal component square plus tangential component square. I will try to see one last example here. The example here is that of a roller coaster which is going along this blue dotted line. We consider it to be a point for all practical purposes and assume that this point is going along. Y is 1 over 100 x square, and it is going at a rate of 6 minus 0.06 meters per second square acceleration, and we need to find its acceleration when it reaches a point B, where SB, this distance, is 40 meters. Let us try to do it step by step. I'm kind of showing each step in a box so that we know what is the sequence of computations that we need to do. By the time it reaches B, its acceleration ATB is 6 minus 0.06, where S is equal to 40 meters. So if you substitute this, you have 3.6. And then we use the relation integral AT ds is integral v dv to obtain vv to be 19.59. As you notice, I'm kind of trying to give an outline of the solution and let you compute the final result and verify whether everything is fine or not. Then we'll find out what is the radius of curvature at point B using the equation y is 1 by 10 x square, and then we'll compute normal component of acceleration, and then we'll write total acceleration is under root sum of tangential component square plus normal component square. We'll see the next topic, that is polar coordinates and cylindrical coordinates, in the next lesson.